All right. Welcome to an extension of the standard model episodes that we've been recording. And this one is going to focus particularly on neutrinos. And I actually really enjoyed getting into neutrinos. I didn't think I would. I thought they were kind of boring before I looked into them. And I mentioned this to you, Zach, earlier. If I went back to grad school and did another PhD in physics, I think it would be in neutrino physics because I think they're that awesome. So, yeah, I'm super interested in learning more about neutrinos and sharing what I've learned so far. But I'm definitely not an expert. And I just have really enjoyed digging into this beyond just YouTube videos and Wikipedia pages, but actually finding books on, starting from standard model books and getting into neutrino-specific books. I found the topic really interesting. So hopefully the listeners enjoy it as well.
Yeah, didn't quite have the money for it, but there was just that History of Neutrino conference in Paris on September 5th. Yeah. Which would have been great to go to.
Not quite in the hyperfine budget.
Yeah. Send us money and maybe we'll go next year.
Yeah. Yeah. So I think we can start with some basic just history of neutrinos. Maybe most everyone knows this already, but just where it comes from, why it even is a thing, and why it's interesting and how it fits in the standard model. So originally, in 1930, people were observing beta decays. So something that emits an electron from a nucleus through some decay, usually like a proton into a neutron or vice versa. But something that comes out of it is an electron. And measuring the energy and momentum of that electron, there were some missing energy and momentum in the decay process. And so Wolfgang Pauli in 1930 proposed that there's a particle that we're not seeing, that we don't know about yet. And that's probably carrying away the extra momentum and energy that's missing from this decay. So he called it actually a neutron back then. 2 years later, Chadwick found what we now know as the neutron and called it the same thing. And they were actually, Wolfgang Pauli thought it was the same exact particle. He thought there was one neutron, which was the thing that came out of the beta decay, and then also the thing that Chadwick found. And then people started realizing, no, there's two separate particles here. The thing that's coming out of the beta decay is much smaller than what we now know as the neutron. So Fermi, an Italian physicist, used the word neutrino at the Solvay conference in 1932. And so he wasn't the first one to say it. Someone made up the name neutrino in a conversation with Fermi, but then Fermi kind of popularized it at the conference, and Pauli started using the word neutrino as well.
Right, which is like the Italian essentially is like little, right? The suffix like, there. So it's like neutron and little neutron.
Mm-hmm, exactly. Yeah. So, and the guy that came up with the name, he was Italian also, and talking to Fermi, who's Italian. And so he used the diminutive ino at the end of the word to make it sound like the little neutral one. So that's what we have, is the tiny neutral particle, the neutrino. So in the standard model, we have 3 neutrinos. And does that mean that there are only 3 neutrinos? Probably, but we don't really know. But what are the 3 types? They are paired up with the other leptons in the standard model. So we have the electron and the muon and the tau particles. So those 3 particles each have their paired neutrino versions. So they have the electron neutrino, the muon neutrino, and the tau neutrino. And the way that they're distinguished is in an interaction, a weak interaction, which is how we detect neutrinos at all, is if a neutrino slams into a nucleus, an electron neutrino can only turn into an electron. And so you detect the electron after the neutrino collides with the nucleus. And the electron neutrino only creates electrons. The muon neutrino creates muons, and the tau neutrino creates tau particles. So those are the things we actually detect. We don't detect the neutrinos directly in those processes.
Yeah, it's kind of interesting. You can go and look at these older film pictures of bubble chambers and stuff of when they have like a beta decay or something. and you can see tracks for like the beta particle, the electron that gets emitted, but there's like weird kinks and stuff that like shouldn't be there. And they that's kind of part of it too, is they said like, we have to conserve momentum here. Like there must be something that's just not leaving a track here. In order to like leave a track in a bubble chamber, you have to have a charge. So there must be like a non-charged thing here. But it's kind of interesting just to say that like there was nothing there in the picture, but they were able to identify that there was something there at the same time.
Right. Yeah, by the thing being missing, like that told us there was something else we just can't see in our experiments. Right. So we have those three types of neutrinos, and it's kind of interesting that we know that there are only three nearly massless neutrinos. The neutrinos are extremely massless, and we actually thought they had no mass until somewhat recently. And even when I was going through school, the textbooks that I used, the neutrino was zero mass in the books. I think probably a caveat of like maybe zero mass. But since then, we've learned that they actually do have mass, and some people won a Nobel Prize for that, but we know they have mass through something called neutrino oscillations, which we'll get to in a little bit. But basically, neutrinos can change when they're emitted. They can start off as an electron neutrino, but then as they travel, they can change into a different type of neutrino. So they can oscillate around. They don't just go from electron to muon neutrinos and stay there. They oscillate back and forth. And they oscillate between all three of them. But how do we know that there are only three? We know by studying the lifetime of the Z naught particle, so the Z0 boson. We know that the lifetime of that particle depends on how many neutrinos there are. And we've measured the lifetime of that particle, and we fit models with two neutrinos, which, I mean, we've observed three of them in experiments, but let's say there was two, and we try and fit the data for a two neutrino standard model to the Z particle's lifetime. It doesn't fit. And then say if we do it with four neutrinos, some made up system of physics with four neutrinos, we try and fit that to the Z particle's lifetime. It doesn't fit. Three is the little, Goldilocks perfect magic amount of neutrinos that gives us the proper lifetime that we've observed for the Z particle.
So does this particle decay into three neutrinos, or?
No, it's I think it's more complicated than that. I don't actually know, but it's more just like, if there are two neutrinos, let's figure out all the physics around two neutrinos. Like, what would physics look like in that situation? Right. And then at some point you reach the Z particle by saying like, if this, then this, then this, then this, then this, and we're at the Z particle's lifetime. And so the two neutrino physics gives us too short of a lifetime. The four neutrino physics gives us too long of a lifetime, and three neutrinos is spot on, exactly what the data shows for the Z particle.
Right. That's kind of like a pretty good example too of like theoretical physics in action in the first place, right? Like that's a really, they postulate these things that aren't in, standard physics, like, hey, there's four neutrinos, and then arrive at some conclusion and see if that can explain something, or if it's, absolutely wrong. Like in this case, it's like, okay, well, that would mean that this Z0 particle would have a different lifetime than what we're measuring. So we're pretty confident then that there's four neutrinos, or three neutrinos, not four. Yeah.
Not four. Exactly. Yeah. It's kind of cool just starting from postulates and saying like, okay, if this, then what? And then you do science and figure it out. So I should specify that limits us to three nearly massless neutrinos. So three very light neutrinos. What is also possible is that there are more neutrinos, but they're just very heavy. And the physics of this Z lifetime thing isn't so much affected by those heavy neutrinos. And we'll talk about what types of neutrinos those could be. There's a few options for extensions to the standard model in the neutrino physics area, where we have some really heavy neutrinos. So we know the neutrinos aren't massless, but it is very light. But what's interesting is there are so many neutrinos that they make up about half the mass of the universe. Like, think about, like, look around you. You don't see neutrinos anywhere, and all the stuff around you has mass. but double it, and you have that many neutrinos just out in the universe.
Yeah, isn't there like, I always remember reading or hearing like, if you look at your thumbnail, there's like some huge number of neutrinos passing through your thumbnail, like at any moment in time.
Every second. Yeah. I don't know the number, but yeah, it's something like billions of neutrinos through your thumbnail, like just passing through you. We never notice them. It's a ridiculous number of neutrinos, and most of them for us on Earth come from the sun. So the sun produces a ton of neutrinos through beta decay. And we are just completely bombarded with neutrinos all the time. And they don't interact. They rarely interact with anything. Every once in a while, they'll slam into a nucleus and interact via the weak interaction, which is the only way we detect neutrinos, is them touching something and interacting through the weak interaction. They don't interact electromagnetically because they're not charged. They don't interact through the strong force because there's no flavor charge. Like they're not the charmed or strange and that kind of stuff. Red, green, blue. So they don't interact through those two forces, electromagnetic and strong, but they do interact through the weak interaction, and that's basically it. So, since they are so rarely interacting with things, we actually set up detectors that run at nighttime in particular, because we want to have them pass through the Earth first and then hit our detectors on the dark side of the Earth. Like, so at nighttime, we're running neutrino detectors because passing through the Earth actually helps us kind of tamp down I think it's just the barrage of neutrinos. We don't want too many neutrinos. I honestly don't know, but I know. Sorry, let me rephrase that. It's not dark side of the Earth. We set up neutrino detectors on the opposite sides of neutrino sources, so we can have them pass through the Earth and actually detect things on the other side of the Earth from the source of neutrinos.
Right. Well, like you were just saying, though, like the biggest source of neutrinos for us is the sun, right?
Right. Yeah. But why do we need to have it pass through the Earth? That's what I'm not 100% sure of. I've heard that that's true, but I don't know if that's true actually.
I mean, I can imagine it might just be like a signal to noise kind of ratio, or like, because maybe, the Earth is going to attenuate neutrinos some small amount, and so that must have something to do with it. Versus like there's extra galactic neutrinos as well that are hitting. So maybe one of those things is, the ratio of those things changes depending on whether you're, in daylight or in nighttime.
Right. Yeah. I'll have to double check that. We might cut that out, but yeah. So the way we detect them is neutrinos slamming into a nucleus, and we typically just have a huge high density uniform type of material, and one of the types of materials is just straight ice. Like in Antarctica, they just carved out a block of ice and put detectors around it and say, okay, if a neutrino hits one of these pieces of ice, we'll detect it, because there is so much ice in this block that's just enormous. It'll interact with one of them, and we have enough detectors surrounding all this ice to see if it happens. And that experiment's called Ice Cube, which is nice.
Clever. I mean, I think that's really impressive to think about in general, just that, like, how sensitive does that equipment have to be in order to detect, this nearly massless particle hitting a thing? I mean, that kind of makes it sound like it's a momentum thing, and I have no idea if that's what it is. I doubt it. But, just like to be able to separate, a particle that can pass through the entire Earth, like without interacting with anything, like be able to separate that thing hitting your ice from like, a little bit of air or something, or like a piece of ice melting, or, some other, more common thing that could happen. Like that's a really impressive, like, feat of engineering physics. Right.
Yeah. Yeah. And these other things, like just volumes of oil, I think they want to get a lot of hydrogen atoms, so they use some hydrocarbons in the oil. that interact with the neutrinos every so often. And water is just another one. You just fill up a huge tank with water. You might have seen the picture if you look up Neil deGrasse Tyson floating on a boat in this, like, looks like a big bubble. Like, it's a big circular tank, and then there's little bubbles all over it. Those little bubbles are the detectors that are measuring the neutrino interactions through some sort of scintillation that happens.
And don't they do these in mines as well?
I think so. Yeah, they're all underground, and the reason is that they want. Maybe this is what I'm getting at as to the dark side of the Earth. We get some neutrinos from cosmic rays interacting with stuff in the atmosphere, and so if we don't want to measure the stuff that, like, we don't want to put a detector on the surface of the Earth. We want to bury it deep. How deep do we want to bury it? Well, we can bury it on the other side of the Earth and measure the neutrinos from the sun only, and not pay attention to the ones that come from the atmosphere. And so we'll know that directionally we're getting the solar neutrinos in particular, as opposed to the atmospheric neutrinos. So I think that answers the other side of the Earth question. Does that make sense? Yeah.
Because I mean,
we want to bury it and get away from the atmosphere. How far can we bury it? Well, we can just go to the other side of the Earth.
Right. It's like that problem of, like, you know, who can build the largest area fence, and you, like, build the fence around yourself and then define yourself to be outside. Like,
right.
Yeah. But no, yeah. I mean, like, because, you know, in addition to neutrinos as well, like, there's, you know, a bunch of particles bombarding the atmosphere. And when they hit the atmosphere, you get this kind of shower of particles. You know, muons come down from that. And I don't even know all the particles that do, but you kind of get this cascading shower of things that come down. So I can imagine part of burying it deep is, you're limiting the number of those that you're going to see.
Right. Exactly. And so the important thing is solar neutrinos are the ones that we typically measure. The reason we do that is because we understand solar physics really well. So we have a really good grasp on the types of nuclear processes that happen in the sun, just based on the elemental makeup of the sun. So we know what types of nuclear reactions happen, what types of neutrinos come out of the sun, and how often, basically. And so what we can do is count the neutrinos that come from the sun and compare that to what types of neutrinos we expect to come from the sun. And what I mean by that is we have 3 types of neutrinos, and we have electrons, muons, and tau neutrinos coming in from the sun. But if we count, say, 10 electron, 6 muon, and 4 tau neutrino types, whatever, I'm making up units, whatever, billions, trillions of each ones of those, but we expected not 10, 6, 4, but maybe 8, 8, and 6, or something like that. We didn't measure what we expected for each type of neutrino. That's a problem. And it's either a problem with our understanding of solar physics, or it's a problem with our understanding of neutrino physics. And that happened, I think, in the 70s. They started measuring this stuff and saying, hey, we're missing some neutrinos that we thought we would have. And so they started redeveloping their solar physics. And then they kind of were like, no, it's not the solar physics problem. We got that down pretty well. It's the neutrino physics. We don't understand neutrinos well enough. So something else is happening. And that led them to start thinking about maybe what's coming out of the sun, which might be a lot of electrons and then not very many muon or tau neutrinos. They start changing flavors. So they turn into, from an electron, they turn into a muon neutrino on the way from the sun to the Earth.
Right. So just like spontaneously, you have a electron neutrino coming at the Earth, and then, 1 second, and then the next second it's a muon neutrino.
Right.
Exactly. Just something like that. Yeah.
Yeah. And there's enough. I mean, these things are very, very close to massless, and they're so close to massless, we thought they were traveling at the speed of light. So what's the time delay between the sun and the Earth?
Like, do you know, Zach? Minutes.
I know it's 8. I couldn't remember if it was minutes or seconds. I don't know. I think it's minutes.
Yeah. I think it's minutes.
So if they were massless, it would take them 8 minutes to go from the sun to the Earth. They're very close to massless, so it's very slightly less than what it would be if it was traveling at the speed of light, a little less than 8 minutes maybe. But that's enough time for them to start changing from one type of neutrino to the other. And so the neutrino physics that was developed to explain that came down to it depending on the neutrinos actually having mass. If they have mass, then they can change their flavor. If they're massless, the neutrinos can't change flavor. And that's how we discovered that neutrinos have, in fact, mass. They're not massless.
And this is a like fairly new development, right? Mm-hmm. It wasn't the Nobel Prize award for this in like 2000 something, 2000.
Yeah, pretty recent, like 2010, somewhere around there, plus or minus 3 years. That's my guess.
Yeah.
So they got a Nobel Prize for working this out, not only experimentally, but also theoretically. And it's kind of an interesting way of thinking about neutrinos. So there are different neutrino states that mix together to produce the neutrino particles. So the particles are the electron, muon, and tau neutrinos.
Right.
The states are states of definite mass, which you can just label 1, 2, and 3. Okay. So there's 3 mass states that mix together to give you 3 particle states. Now, it's kind of weird to think about, but we can divide a lot of different things into different categories. Like people, we can say there's 3 different types of people. There's young people, middle-aged, and old people, right?
Sure.
And we can say there's short people, medium people, and tall people, right?
Right, yeah.
But what's different is with a person, you can definitively say that person is old and tall. And it's not a mix of any of the other ones. It's not old and short, medium, tall mixed, right? It's just old and tall.
Right.
Neutrinos don't work like that. It's a quantum superposition, meaning the neutrinos, if it's an electron neutrino, it's not electron neutrino and mass 1 level. It's an electron neutrino and a mix of mass 1, 2, and 3. We don't know which one it is. And if it's a mass 3 neutrino, it's a mix of electron, muon, and tau. So that these mixings happen between all 3 states and all 3 types.
Wait. So can I say that?
Sure.
Back to you. So it's not like so we have 3 neutrinos.
Mm-hmm.
And each one of those neutrinos have different mass. But
no. So
this isn't what you're saying.
That's not what I'm saying.
Wait. Okay. All right. No. Okay. All right. Yeah. Okay. I'm giving up. All right. Say it again one more time.
There's 3 particles: the electron neutrino, muon neutrino, tau neutrino. How do we know if it's one of those 3 things? Because in a beta decay, if a neutrino slams into a nucleus, that's an electron neutrino. We get electrons out. We don't get a muon out from electron neutrinos.
Gotcha.
So that's a definite particle state of the neutrino. In addition to those 3 particle states, there are 3 mass states.
Okay. All right. So I think I got it. Let me say this back to you for clarification. Mm-hmm. Okay. We have 3 negatively charged particles: the electron, the muon, and the tau. Right.
Correct.
And those are all 3 identically the same, except we can determine what they are by looking at their mass. Right.
Right. Yep.
But what you're saying here is you have these 3 particles, and the 3 particles, they might have the same quantum numbers and stuff, but the mass is not distinct per neutrino. It can be, an electron neutrino can be mass 1, mass 2, or mass 3.
Exactly.
Okay.
And when you measure its mass, if you were to actually go and probe it and say, put it on a scale and say, what is your mass? You will get only one mass. This is a quantum superposition. So you get one of the masses every time you do the measurement, but it's just a probability of which mass state you measure for the electron neutrino each time you measure it.
Right. So like each time you're measuring it, you're not measuring the same. You're not always measuring one for the electron neutrino. Sometimes you measure one. Sometimes you'll measure two.
Yep.
And other times you'll measure three. But you're always measuring one of those things, not like any combination of them.
Exactly. So, and I should say, yes, what you said is true for the electron, muon, and tau. Kind of. They all the particles in the standard model do mix to some degree. And we have a really, really good understanding of the quark mixing. Like a bottom quark, sometimes when you observe it, is in a different state than just like the bottom quark is a mix of a few other things. And every once in a while, you might measure the other thing when you expect to see a bottom quark.
Right.
So the quark angle, it's actually really small, but there is an angle that's the mixing angle, they say, for these things called the Cabibbo angle. And that's known for quarks. And it's small. The equivalent thing for neutrinos, I couldn't find out if this is actually known yet. And I don't think it is. I don't think they know exactly how these states mix. But they do know that they do know that they mix. They just don't know exactly how much. And there's different mixing angles between the three different states. Like you can imagine angle between 1 and 2, angle between 1 and 3, and angle between 2 and 3, something like that. Right? So there's three different angles between the three different states. And I think they're working out what those angles are. I don't think those are known right now. Okay, so the interesting thing is the way this leads to the whole oscillation business is let's say there were only two states because the math is a little bit easier. Let's say you start with an electron that's made up of a little bit of mass 1 and a little bit of mass 2. And the angle that you could work out, the way the angle, when I say this mixing angle, the way it works out is you say the electron neutrino is neutrino 1, mass 1, times the cosine of that mixing angle, plus mass 2 state times the sine of that mixing angle.
Right.
So you have this like sine and cosine mixing, and you can imagine taking the, mod square, what's the probability of finding them? They all add up to 100% probability. And that mixing angle is now fixed for each state, meaning there's a cosine of a certain angle. I'm going to make up a number. Say it's 25 degrees.
Okay.
And then you have plus state mass 2 with sine of that 25 degrees. But here's the weird thing. Since the different states are different masses, and this neutrino is traveling from the sun to Earth, the different masses mean that they travel at different speeds.
Ah, interesting.
This is where it starts getting weird. Now, depending on where you are when you make the measurement, maybe by the time it gets to you, the state 1, it's not that it hasn't reached you. It's not that there's like a time delay, but it's this mixing thing that happens. And the angle is now kind of like cycling through the different states. And when you measure it, maybe mass 2 and mass 1 cancel each other out at that particular place where you're measuring it. But where did they go? They actually turned into the muon neutrino. And the muon neutrino is the perfect exact mix that completes, all the neutrino state possibilities with the two states. The muon neutrino is mass 2 times the cosine of that same mixing angle, 25 degrees, minus mass 1 times the sine of that mixing angle. And you can kind of work out the signs and like plus and minus signs and the cosines and sines, thinking about like all the possible combinations of these two mass states making up these two particles, which have to be my dog's squeaking her toy.
Okay, I was like, is that me?
Which have to be linearly independent, and they have to span the space. So what happens is when you make a measurement of what you thought was an electron neutrino, because the fact that the different states move at different speeds, you get these cancellations and additions, kind of the superposition of states changes from an electron neutrino to a muon neutrino when you make the measurement. And it all comes down to the states having different masses.
That's complicated.
It is complicated. Yeah. Yeah. It's complicated and awesome. and I love this stuff. Not that I understand it, but I like to think I understand it.
Well, you definitely get it better than I do.
Yeah, I have pictures in my head that I can't convey perfectly speaking the words, but yeah. Think about waves, superpositions of waves. You can think of like the way we think of like beat frequencies. If the masses are different, maybe you can imagine the wavelengths being a little bit different.
Okay.
And at some places they constructively interfere, and at other places they destructively interfere.
Right.
So the electron neutrino is made up of two different waves which have these beat frequencies. Some places it's constructive interference, it's 100% electron neutrino. Some places it's destructive interference, where the two mass states waves cancel out and you get 0 electron neutrino. But then if you work out how the muon neutrino, its waves constructively and destructively interfere, anytime you get destructive for an electron neutrino, you get constructive for a muon neutrino. And because of the way the two equations, the linear combinations, are set up.
Okay, all right. So it's okay. So this is kind of exactly what we started describing. Is it's oscillating back and forth between these two states. So, but I mean, I guess the thing that I'm kind of confused about, and then is like there's the masses. That the mass state, but then there's also a neutrino state, right? Where it's either
I'm calling it a particle state, like
a particle state.
Yeah. So the way I wrote it out and the way I picture it is there are neutrino particle states and there are neutrino mass states. Okay. And I kind of started using the shorthand mass state for shorthand to make it shorter. But it's the neutrino mass states. It's still a neutrino. It's a type of neutrino. The observation of what type of particle are you is similar to saying where are you in quantum mechanics, and the question of what is your mass is similar to what is your momentum in quantum mechanics. In that, a measurement of what type of neutrino and a measurement of what is your mass. Those two observables, those two measurements are incompatible in the same way that what is your position and what is your momentum is incompatible. And it's a type of Schrodinger, it's a type of uncertainty principle.
Huh, okay. So but it seems like we always know what the particle is, right? Like wouldn't we always know, this is a electron neutrino by its interaction with the nucleus or whatever?
Yes, but then we lose information about its mass. We don't know what its mass is. And if we tried to measure the mass directly, we would lose information of what type of neutrino it is.
Oh, wow. Interesting. Okay.
Yeah.
This is clarifying. It's mystifying, but also clarifying what you were saying.
Yeah. Yeah, these are incompatible observables in quantum mechanics. Yeah, I agree. It's not 100% in my head, but that's the way I'm thinking about it, I think is correct.
Right. And then then it just works out like what you were saying, just to be that you kind of get this constructive interference, and when the other is having a destructive interference, so you get like an oscillation, a full oscillation between this particle and that particle, but then you can also like find it somewhere in the middle.
Right. Yep. Yeah. So,
and this is only possible, right, if neutrinos have mass.
Right, and it all rests on those mass states being different masses. And if the neutrinos are massless, then none of this would happen. Like there wouldn't be this mixing of mass states. There are no mass states. It's just the neutrino, and it's massless. And there's 3 neutrino particles. But because there are these mass states which mix in this particular way, this leads to the neutrino oscillation happening.
Right. Wow. I have no idea how we figured that out. That's impressive.
It's one of those, like, when you look backwards, you're like, okay, I can see how it's true, but how do we know that this is exact? Like, why is this the made up version of physics that is the correct version of it's because, the oscillations happen because it has mass. Like I don't know if I actually could, but you could imagine someone making up other creative ways to lead to neutrino oscillation. But like the fact that it's a definitive, yes, this is exactly right. This is the reason neutrinos oscillate is because they have mass and there are these mass states. Like, why did that one just become, that is absolutely the truth? I'm sure there's reasons, and people know this well enough to give Nobel Prizes for it. Like the people, that's the cool thing about the science and the physics of it is somebody comes up with this idea and then they go through all the implications and say how this fits in with the things we already know and explain the things that we've not been able to explain before. And then you get a Nobel Prize.
Yeah. Do you know, I think this is right, but correct me if I'm wrong, that we knew about neutrino oscillations prior to neutrinos having mass. Is that true?
As I understand it, yes. And I forgot what the term was, but there was a term for like what I was saying about the solar neutrinos being the wrong type.
Uh-huh.
It's like the solar neutrino gap or something like that. Solar neutrino problem. Yeah, I think it was just called the solar neutrino problem. And then, the Nobel Prize for solving it. Yeah, I think it's the 2015 Nobel Prize.
Yeah, that's what I'm reading. I don't know when they performed their experiment, but yeah, the prize came in 2015.
For the discovery of neutrino oscillations, which shows that neutrinos have mass. 2015. Takaaki Kajita and Arthur B. McDonald split the prize. So yeah, 2015 is when they got the Nobel Prize for that. So pretty recent. So yeah, that's the story of the neutrino mass and the oscillations, which are, I think, pretty interesting. But what I want to say is that it's not specific to neutrinos, that this does happen for the other particles as well, but not to the extreme that it happens for neutrinos. There are other particle mixings for quarks, like I said, for the Cabibbo angle. And yeah, I think it's pretty interesting. They study the solar neutrinos to get a good understanding of their source, but then they also have places that make exclusively, just about exclusively, muon neutrinos. So they have nuclear reactors that spit out muon neutrinos, and they literally just plop a detector down next to it, and they just study the muon neutrinos and count those and see if there's a change, and there is.
The thing I think is kind of funny is that there's, like, how do you not somehow always study solar neutrinos? Like,
yeah,
because they could go through the Earth, like, right.
That's what I mean. Is they put a detector near a nuclear power plant that's putting out, or a reactor that's putting out like a huge number of neutrinos that swamps out the number coming from the sun. So
do you know, like in that, I mean, okay. Do you know that, like, if in that case, when you have, this huge number of muon neutrinos, is the only reason, like, we're always seeing them as muon neutrinos is just they haven't had enough time or distance to do any sort of oscillation? Or, like, maybe we just can't tell the difference because we're not isolated enough? Well,
they do oscillate, like, and then they measure that, like, and it's a short enough distance that it's not a lot of oscillations, but there's enough of them that they count the difference and they recognize it. Like, they identify that the muon neutrino changed into electron neutrino, for example. And they would say, oh, look, we have more electron neutrinos than we thought we did based on the source of these neutrinos. So they must be changing.
And then at the same time, they're having to filter out all of the neutrinos coming from the sun.
Yeah, yeah.
Which is, or extragalactic, extrasolar neutrinos as well. Like that's
right.
God, this is just an insane, like, area of physics.
Yeah, it's pretty ridiculous, and the numbers involved are just huge, but also small at the same time. Like, you don't get that many reactions. I want to say on the order of, like, tens of neutrinos get detected, like, in some experiments. Like, yeah, that's ridiculously small.
Yeah, it's no LHC.
Right.
They have like more data than they know what to do with.
Right. Well, yeah, it's just, you got to filter out all the background. Yeah. Ridiculous statistics for sure. Yeah, let's move away from the neutrino oscillations, and I wanted to discuss another aspect of neutrino physics, which gets into some beyond the standard model of particle physics. So this is some stuff that's certainly not verified, and they're kind of ideas floating around, which I think is an interesting way to think about how scientists work. I'm saying we like I did this, but collectively scientists are comfortable being unsure of what's actually happening, and we're comfortable holding multiple solutions to things in our head at the same time without knowing which one is the correct solution, and putting evidence against each of those different things until it's shown that it's not true, or it's shown that it does withstand all the evidence that's been thrown at it as we gather more and more evidence, right? So now we're getting into some places that are in that realm where it's like, we don't know if this is true, but it's a possibility. And so let's hold on to this idea and keep running tests. Maybe they test them directly, or maybe we read a paper that's talking about something tangentially related, and then we can, in our brains, go like, hey, wait, does this fit in with what we're potentially thinking is true over here? So the next little bit is getting into sterile neutrinos.
Right. So yeah, I kind of wanted to just maybe talk about in no detail, but like what you were just saying, like I think a really good example of that is magnetic monopoles.
Mm-hmm.
Just because like we haven't ever seen a magnetic monopole,
right?
But there's no reason, like we can't find a reason why they shouldn't exist.
Yeah.
And so, people are still looking for them, trying to detect them now.
Right. That idea is still sitting in scientists' heads, and they keep it in mind just as they go through doing science, and they'll be like, wait a second, this is about the monopole deal. And then they go back and look at the notes and say like, yeah, this is fitting in with the monopoles or not, which it's been not so far. So it's still there, though. It's still sitting there.
Well, I don't know that we don't have to talk about this too much more, but I don't know if it's that things aren't fitting in. It's just that we haven't seen it, but there's my understanding is that there's no evidence for them existing, and there's no evidence against them existing.
Except that we don't see them.
Right.
Yeah. Yep. Yeah. Very true. So yeah, this is an example of something that we don't know if it's true or not, and it's beyond our understanding of particle physics, but it's a possible expansion of our understanding of particle physics. So physicists do look into this kind of stuff. So this being the sterile neutrinos, and the word sterile is with regards to, like I said before, neutrinos are uncharged, so they don't interact through the electromagnetic force. They don't have any flavor charge to them, so they don't interact through the strong force. Neutrinos in the standard model interact through the weak force, but, and this is the interesting part, the sterile neutrinos don't even do that. They literally don't do anything. They interact through, bending of space-time and gravity, but they don't interact electromagnetically, strong force, weak force, neither of those.
So this is some type of neutrino hypothesized that could exist. That's just, we just we can't observe
no
interactions with stuff, pretty much.
Exactly. So the interesting part is each fermion, remember fermions are the massive spin 1/2 particles from the standard model, like electrons and quarks. Each fermion in the standard model has 4 versions. And we've talked about 2 of them often. One is matter versus antimatter. So every electron in the standard model, there's 2 different types, matter and then antimatter. And then in addition to the matter and antimatter split, there is a chirality split. Left and right, chiral. electrons. Every fermion has that split.
Okay.
So what is chirality? It's difficult to explain.
I mean, I think the easiest way to think about chirality, like in general, not specifically pertaining to neutrinos, is, it's the fact that you can't ever take your hands and you can't overlap one on the other in the same direction to get your other hand, right? They are mirrored images of each other.
Yeah.
And therefore they're chiral. There's no, normal transformation you can do to make your left hand into your right hand.
Right.
Without the use of like a mirror.
Exactly. So yeah, it's all about the mirror image of these particles. And mathematically, it fits into I don't know how to pronounce the name, Poincare group. But it's a mathematical abstraction. But the key thing is it's intrinsic to the particle. Like it doesn't depend on what you're doing when you make the measurement of the chirality, I guess you could say. So it's an intrinsic thing that's built into these particles. And we talk about something being left chiral or right chiral. And like what Zach said, it has to do with the mirror image of the object, how that's affected. And as far as we know, all fermions, except neutrinos, and I'll get to that in a second, all fermions, the matter can be left hand or right hand chiral. And the antimatter can be left hand or right hand chiral. Good so far?
Yep.
Okay. In weak interactions, only left-handed matter interacts through weak interactions, and only right-handed antimatter interacts through weak interactions.
Right. Yeah. So like when we see beta decays, it gives off a neutrino. Mm-hmm. It's always, or an antineutrino. Right. The neutrino is always left-handed, or the antineutrino is always right-handed, as far as we can tell.
Right. But there are right-handed electrons. But the problem is, since we only observe neutrinos through the weak interaction, right-handed neutrinos don't fit in the standard model, because right-handed matter does not interact through weak interactions. And weak interactions are the only way we observe neutrinos. Does that make sense?
Right. So yeah, there's left and right, electrons, I guess, mm-hmm. But they don't interact through the weak force. They do to some degree, right?
The left electrons do, and the right positrons do. Those two interact through the weak interaction.
Gotcha. But the right-handed electrons and the left-handed positrons, they interact through other forces,
other stuff. We observe
not
them
through the weak.
Exactly. We observe them through other things, but not the weak interactions.
Okay.
And since neutrinos, we only observe them through weak interactions. Like that's all we have left, really. We don't know if the right-handed neutrinos and the left-handed antineutrinos exist, because there's no way for us to observe them. So
sounds like a dark matter.
Well, I didn't say it. Zach said it. People get mad when you just say that just because it's something that you don't know what it is and it doesn't interact. But maybe. My actual, I don't know. It's not a bet, but it's a hope, I guess, is that the next type of neutrino I'm going to talk about. But this is an option. Yes, people say maybe sterile neutrinos are the dark matter candidate. We don't really know. And another nice thing about them is they're actually a little bit more massive. They're not as massive as the next type of neutrino I'm going to talk about, but they are more massive than the standard neutrinos in the standard model. Good?
I wonder if there's like any thoughts about another force existing that like only, left-handed matter interacts through. Like a left-handed weak force or something. Yeah,
it's possible. And that's, I don't know if it's a different force, but the way the particles gain mass, the way we understand them gaining mass, most people these days know it's the Higgs field. But what about the Higgs field is that the fermions gain mass by oscillating their chirality between left and right through an interaction with the Higgs field. So they switch from left and right, kind of like how we were talking about the neutrino types, maybe being a state that's a mix of the two different mass states, and they oscillate between the different particle types. Like I was saying before, this is a different oscillation, but it's the same basic principle. They're a linear combination of two different things, and then they mix back and forth between them. They oscillate, and that leads to the particles, the fermions, having their mass.
Okay.
But since the neutrinos, we don't know if there's the right chiral normal, not anti-neutrino. We don't know if that even exists. Does it gain its mass through an oscillation of chirality and interacting with the Higgs field? That's something we don't know. So there might be another mechanism by which the neutrinos gain mass. Because we don't know if that other thing, that there's anything to even oscillate into, basically. Right.
And well, so here's a question, a thought, maybe. I don't know if you can answer it, but so I'm reading through Griffiths. When he's talking about like parity and stuff, he references, like all, well, he starts by saying, assume neutrinos are massless. And then he says, okay, now when we go that route, then we can say, hey, all left-handed, or all neutrinos are left-handed.
Okay.
But then he goes, wait, but if they have mass, that means they're not traveling at the speed of light. Therefore, if I'm traveling faster than a left-handed neutrino, then it's going to look right-handed as it's, as I'm passing it.
Right. So yeah. Right before we hit record, for the listener, I told Zach, I'm like, I have a question that I need to Google real fast, and it was this question.
Oh,
everything you're saying is correct, but the word that describes what you're talking about is helicity, not chirality. So helicity is what you're describing. It's the spiraling motion, like the direction of the spin, like as the particle rotates, quote unquote. Project that onto the particle's momentum as it's moving. So imagine like a football spiraling in the direction, to the right, let's say. Take your thumb from your right hand and curl your fingers around. So your thumb in your right hand points in the direction the football's moving. Your fingers curl around in the direction the football's spiraling.
Right.
If it's your right fingers that curl in the direction that the football is spiraling, that's a right-handed helicity for that particle. If in the other instance, the football is spiraling the other direction, like if one was clockwise, the other was counterclockwise, meaning you need to put your left thumb in the direction the football is moving and your left fingers rotate around in the direction the football is spiraling, that would be a left helicity for that particle. So that's the thing, that if you're moving faster than the particle, if it was moving with right helicity and then you went faster than it changed to left helicity, that is not an intrinsic property of the particle, but something that's extrinsic. It depends on what you're doing when you look at it. And yes, it would change. And that is the question that I was trying to Google quickly before we hit record is, wait, when I say matter is left-handed and antimatter is right-handed for neutrinos, and there are no right-handed matter neutrinos in the standard model, is the right-handedness talking about chirality or helicity? And that's the answer I couldn't find.
Interesting, because I'm looking at Griffiths right now, and he has this big, neutrinos are left-handed, anti-neutrinos are right-handed in these big bold letters. But you're right. In all of this, he is referencing helicity.
Right. Yeah, and I think it's chirality. I honestly, I don't know. And if you go to my awesome, amazing source, Wikipedia, if you go to sterile neutrinos in Wikipedia and search for the word helicity, it's all in this, every instance of the word helicity is in this paragraph and the topic of motivation. And then it says, under motivation, see also chirality. And if you search for the word chirality, almost all of those are also in that same paragraph. So let me read the sentence that confused the hell out of me.
Okay.
Experimental results show that all produced and observed neutrinos have left-handed helicities. That's the spiraling football thing. And all antineutrinos have right-handed helicities. Great. I got that. That's so okay, clearly It's talking about helicities. In the massless limit, it means that only one of two possible chiralities is observed for either particle. These are the only helicities, and then parentheses, and chiralities included in the standard model of particle interactions. So it like bounced back and forth between helicities and chiralities in those like three sentences.
I think, but I'm not 100%.
It said in the massless limit. I don't know if that's the key term that I'm kind of brushing over. But
yeah, I think what it kind of says to me is, in massless limit, helicity equals, you only have one type of helicity, therefore, it's the same as chirality.
Right.
You can classify them as either this way or that way. Mm-hmm. So you can classify them as left-handed or right-handed. Right. Whereas if you're not in the massless limit, you can have both types of helicities, which maybe means that there's no chirality in that situation, in the mass situation, but I'm not 100%. That's kind of...
Yeah. So continuing through that little section, it says, all neutrinos have been observed with left-handed chirality, and that word is italicized, chirality. Chirality is a fundamental property of the particle and is relativistically invariant. Whereas the helicity, now this is not a quote, this is me saying that the helicity is not relativistically invariant. Meaning, like what you were saying, if you move faster than it, the helicity changes, but not the chirality.
Right. Oh, yep. Okay. Yeah, it says, I think that this next sentence is the same regardless of, or maybe you said this, I was reading. Mm-hmm. It is the same regardless of the particle's speed and mass in every inertial frame. So, yeah, it sounds like chirality... Yeah, chirality does not equal helicity except in the massless limit.
I see. Right. Yeah,
because you can't Lorentz boost faster than a massless particle.
Yeah. So I guess my fundamental question is right-handed helicity of a neutrino, does that break the standard model, or is that okay in the standard model? I'm pretty clear on the right-handed chirality breaks the standard model, meaning if there was a right-handed neutrino, that is not antineutrino, right-handed regular neutrino, that's beyond the standard model. The standard model cannot account for a right-handed chiral neutrino, but can it account for a right-handed helicity of a neutrino? That I don't know.
So, yeah, I mean, I think right-handed helicity or helicity not equaling chirality is based on kind of what I'm reading. It sounds like it's not yet incorporated in the standard model. Just the second paragraph there. Recent experiments, such as neutrino oscillation, however, have shown that neutrinos have a non-zero mass, which is not predicted by the standard model and suggests new unknown physics.
Oh, that's interesting. So just the fact that the neutrinos have mass at all is beyond the standard model. I didn't know that.
Right, because if it has mass, now you can now helicity is not the same as chirality.
Got it. Okay, that actually clears up everything. I was under the impression that a massive neutrino is still okay, is still allowed in the standard model. Apparently, based on that sentence in Wikipedia. I don't know who wrote that, but somebody wrote that sentence.
Right, there's no citation there. So.
Yeah, there's no citation. Exactly. I'm going to add citation needed, buddy. Okay. No, that kind of clears up what I was questioning. Yeah. So yeah, anyway, that's sterile neutrinos, which I think is pretty interesting. And it's only a question like, do these things actually exist? Because the only way to observe neutrinos is through a weak interaction, which right-handed particles do not interact through the weak interaction.
Right. So just like we're saying, like monopoles, there's no way for us to tell Well, okay, we could tell with monopoles, but like, right now there's no way for us to tell. We haven't seen these things, but in theory they could be there, these sterile neutrinos.
Got it. Yeah.
Right? Like we would just have to find a way to interact with them.
Right. Yeah. We need some other way that they interact. Gravitationally is kind of all we got left. So we need a lot of them because they're pretty low mass.
Right.
I think one video I watched, which is actually a pretty good video, but you got to slow it down, and he talks really fast and brushes over things, and I don't know. It makes it sound like it's not a good video, but it's actually a pretty good video. It's from the PBS Spacetime on, what is it actually called? Will a Neutrino Change the Standard Model? By PBS Spacetime. But yeah, that video goes through the left-right divide, and it talks about helicity and chirality. But I'm sure if I rewatch it now with that understanding, that the fact that it has mass breaks the standard model already, that's what it's talking about. But the new neutrino that he's talking about is this sterile neutrino, which it was believed that it was actually observed in some experiment. But what's super interesting and people criticize their results for is the individual experiment that thought they had sterile neutrinos detected. Do you know the limit for particle physics? Like it's 5 sigma, right?
Yeah, 5 or 6, something like that. Yeah.
I don't remember exactly. I think it's 5 sigma, meaning there's, you have to be 5 standard deviations away from your null hypothesis. I don't even know if that's the right way to say it, but basically you need to be pretty far beyond just like a decent expectation that this is actually correct, what you're observing, enough that it's 5 sigma from that, the normal, non-discovery. So they were not 5 sigma. I think they were 4 point something sigma, not quite 5. But what they did is they took their results and combined them with another experiment, which was under 5 sigma. And they said, okay, if you take both of these experiments and combine the results, then you get 6 point something sigma. Look at that. So people are like, I don't know if that's good science to just cherry pick 2 experiments that kind of got similar results and combine them and then say, look, if we did them both together, it's 6 sigma.
Right.
So it must be true. And then people are like, well, yeah, but look at all the other experiments that said you're wrong and that's not actually a discovery. And combine those with your results, and it's much, much less than 5 sigma.
Right. Yeah, let's just combine everything and see what we get then.
Yeah, exactly. Yeah. I thought that was pretty good. But I mean, they know that, and they like are saying, if we look at things in this particular way, we can get the 6 sigma, which is interesting itself. But yeah, and that's not, a kind of side note that the Higgs boson mass, there were 2 experiments that discovered the mass, and they didn't combine those experiments to get their whatever sigma they needed. They both had their own separate 5 sigma experiments, and they were within agreements of each other. Like they had a number with some uncertainty and for the mass of the Higgs, and then the other one had a different number, but it had also its own uncertainty, and those uncertainties overlapped. And so they said, great, we're in agreement. Perfect.
Yeah, right.
Cool. So so that's sterile neutrinos, which are these right-handed matter neutrinos, which we can't observe because they don't interact through the weak interaction. Now, there's other types of neutrinos that are even more massive. So the sterile neutrinos roughly are on the order of 1 electron volt worth of mass, 1 eV, whereas, most particles like quarks and the electron, I think electrons like half a mega electron volt, something like that. And then some of the quarks are, up into the hundreds of mega electron volts. And a mega is a million. So they're in hundreds of millions of electron volts. And then this sterile neutrino, which is heavier than the normal everyday neutrinos, is 1 electron volt. And so these things are a little more massive, but not nearly, not nearly the most normal typical particles we have in the standard model.
Right.
Okay, now things get interesting. We have another type of neutrino, different than sterile neutrinos. And it's based on this matter-antimatter I guess, distinction, the fact that an electron's antiparticle is different than the electron itself. And in the Standard Model, all fermions are what's called a Dirac fermion, meaning that the antiparticle is not the same thing as the particle itself, meaning that we can discern them. There's differences.
Right, as opposed to something like a photon, where a photon is its own antiparticle. Exactly.
The photon's its own antiparticle, and any sort of interaction or, looking at conservation, stuff like that, if you try to discern the particle from the antiparticle, there's no difference. And electrons can't be their own antiparticle just fundamentally because we need charge conservation to happen. And so the fact that if we, let's say a photon splits into an electron and a positron, right? If it's an electron and an anti-electron, which have the same charge, then we go from zero charge from the original photon into now 2 electrons worth of charge, which is not valid for conservation of charge.
Yeah,
right? We need a negative charge for the electron and then a positive charge for the positron, add up back to that 0 that we started with from the photon. Okay, things get interesting when we consider the neutrino because it is a fundamental particle which is neutral. And since the charge conservation is no longer an issue for its being its own antiparticle, that's now a possibility. So there's other types of fermions as opposed to Dirac fermions, which is every other particle in the Standard Model, which are the Majorana particles, Majorana fermions. Those are fermions which are their own antiparticle. And a neutrino is possibly a Majorana neutrino, and it's spelled Majorana, but it's an Italian physicist who Fermi actually said, once a physical question has been posed, no man in the world is capable of answering it better and faster than Majorana. So he in 1931, Fermi said that about Majorana. So he's had his hand in some interesting physics and came up with his idea of these Majorana fermions, which are their own antiparticles. And it's possible neutrinos are one of these examples, but we don't really know. But what it leads to is something called the seesaw mechanism, like a playground seesaw, which is take the left-handed light neutrinos that we were talking about before.
Right, our standard neutrino.
Yep. And then if there's the anti-neutrino, which is this Majorana neutrino, if that's the antiparticle, if it's a Majorana neutrino, you build up this matrix of these particle-antiparticle masses, and what you end up with is a product of the light neutrino and the heavy neutrino. The product of those things stays constant. Do you know what the geometric mean of two numbers are? As opposed to an arithmetic mean, which is just like the average, like add them up and then divide by the number of things.
Yeah, I'd have to review.
Geometric is take the product of all the things and then take the nth root of how many things you multiply together. Okay. So if you took the ages of two people, the geometric mean is multiply the two ages together and then take the square root.
Right. Okay.
If there's three people, you multiply three numbers together and take the cube root. So that's the geometric mean. So anyway, what ends up happening in the seesaw mechanism is that the light neutrino's mass and the heavy Majorana neutrino's mass, the geometric mean of those two masses seesaws around the Higgs mass. And so you have these extremely light neutrinos balanced by these potentially extremely heavy Majorana neutrinos. And the product of those two things ends up being, the geometric mean of those two masses ends up being at the Higgs mass. So that it's like a seesaw with the Higgs at the middle and these light normal neutrinos, which we observe, heavy Majorana neutrinos on the other end. And those, gotcha. I don't know. I think there's some elegance to that I just really like. I kind of hope those are the dark matter neutrinos because they are going to be so massive compared to the light neutrinos. So sorry, I brought in dark matter this time.
So if these Majorana neutrinos exist, do you know, are they predicted to be a different flavor, so like a new generation of part, or is it just going to be like we're going to have the electron neutrino, and the electron Majorana neutrino?
I think that, and I think what the distinction is it all of this rests around how neutrinos gain their mass. Like in the sterile neutrino case, it was that all the other fermions oscillate between left and right chiralities, and we don't know if the right chiral neutrino exists at all for it to even oscillate into. So maybe there's some other mechanism by which the neutrinos gain their mass, which isn't this normal way that we think about through the Higgs mechanism with this oscillations in chirality. Another way they can gain their mass is through this, I guess you can say, Majorana mechanism, where the math works out that there is this other matrix element in these linear combinations of neutrino states and potential masses that we were talking about before. There's another term in the matrix which used to be zero, but in the Majorana physics, it's not zero.
Okay.
And when you work out the like eigenvalues of this matrix, one of them ends up being this Majorana mass, which could be enormous. And it happens to work out that the two of them seesaw. There's a really light mass, and then there's a really heavy mass. And I'm going to say something that I have no bearing, and I've read nothing about it, but maybe the other particles also have Majorana counterparts. I don't know if that's true, but I don't think it is, but maybe it is. That's me speculating on the basis of absolutely nothing.
Then we'll have another dimension to look at. We'll have our Majorana dimension. Oh yeah.
Yeah. And yeah. But I mean, some of the particles are actually more heavy than the Higgs, so there should be lighter versions of the top quark, for example. If all of the particles have the seesaw mechanism. Again, this is my ignorance speaking because I do not know neutrino physics well enough to say why that's a stupid idea, but I'm sure it is a stupid idea.
But if you guys donate enough money, you can sponsor Derek to go back to college and get another PhD in neutrino physics.
Sitting in grad school again. Fantastic. So yeah, that's kind of the extent of my neutrino knowledge. We got our basic neutrinos, which oscillate between different mass states. We got sterile neutrinos, which possibly have mass in this new mechanism, and then Majorana neutrinos, which are even stranger. But it's all based on some pretty not difficult math. Like it is, but it's not. I didn't have to look at Feynman diagrams and calculate, cross sections of I don't know what's, but yeah, it wasn't too bad. And I say that with a complete understanding that I'm pretty ignorant on all this stuff, but I got I think a sci-pop plus knowledge of neutrinos after doing this research.
Yeah, I'm still trying to wrap my mind around the fact that like neutrinos can oscillate in mass. Like, I don't know, that just feels so strange to me. So like foreign, I guess.
Yeah.
Or, not oscillate in mass, but that they're in a superposition of mass states.
Right.
Like it just seems like most of our daily life, or I mean, not our daily life, but our standard model life that I've seen so far, it seems like the way it's described that, an electron has this mass.
Mm-hmm.
And so I'm like, okay, all right. And then so neutrino has this mass. No, it doesn't. It can have that mass, but can also have this mass or that mass. So wait, but does that mean like the mass of the universe is like change? I guess if the mass is changing, the energy is going to change. Like the motion of the particle is going to change in such a way that it's not going to, we're not going to lose mass or anything. Well, I mean,
I don't think it's any different than think about an electron in a hydrogen atom. It's, what n equals what for that electron. I think it's not explicitly well defined until you make a measurement, right? Like it has a probability of being in the n equals 3. orbital or the n=1 orbital, which are different energies. And you make a measurement and there it is.
Right. But it's just, it's not a, like that state is like, oh, it's, kind of located in this area or follows this wave pattern or something, but wave function. But yeah, to say the same thing for like something with mass seems strange to me.
Yeah.
Foreign.
Yeah.
But it's really cool. Like, I think that's kind of mind blowing.
It is. Yeah. I think it's cool. And, somebody asked a while back on Reddit, what would Richard Feynman find interesting in physics since his passing? Like what would he be particularly interested in? And I chimed in right away and said neutrino masses for sure.
And got a bunch of upvotes.
Yeah. Not that many people chimed in, but yeah.
It's a good question. All right. Well, if you guys have any other, neutrino facts you want us to talk about, let us know. If you want to.
I can Google it pretty quickly.
Yeah.
Because I just dumped everything I know about neutrinos. So I'll be happy to answer more questions. But yeah, it would be me Googling an hour before answering the question.
Right. I mean, but that's kind of the point of the podcast to some degree, is we're putting in effort to condense this into, something that you can listen in an hour.
For sure. Yeah. I mean, I came into the podcast, hit record with a question in my head, and then we worked it out and got the answer. So I'm happy about that.
Yeah. Or, if there's anything else that we overlooked. Yeah. Or, I mean, I guess I'm saying, or if we misstated or anything, let us know.
I'm sure there is.
Find us in the subreddit.
Yep.